So what do you do when you use Bayesian technique in classification? Suppose you have a training set, you have appropriate class labels, means that's what output variable you classified as. You know previously that there are this m number of classes which you a priori you know. Now you have labeled all your outputs. Now for each data item you will look at which class it should belong. Now when you have to learn a specific classifier which will work for any new data, what you try to typically do is you try to identify you try to identify a you try to identify a probability distribution such that the probability of a class given the observed data item, which is the data item in the entire data set, that is the kind of class you will assign it to. So this is what we call as Bayesian classification. It's very simple. Let's look at if a condition of having observed a data set, you are given m classes C1, C2, Cm. You have labeled the classes. Now using this, we try to create a classifier which will basically maximize the class to which it should belong. So let's go with an example, so that way it will be far more clear. Let's take a raw data like this. We have basically trying to create a decision learning algorithm for diagnosing whether somebody is going to buy a computer or not. The output variable, which is a class variable, is whether he's going to buy a computer, yes or no. What are the variables you're looking at? We're looking at age, income, student, credit rating. So what we do is we first look at what is the probability of the outcomes. There are two outcomes, computer yes or no. The probability of C computer buying equal to yes, it becomes C1, which is 9 out of 14. Probability of C2, which is computer buying equal to no, is 5 out of 14, because that's where you see the raw data and you get that, right? Now we try to compute having observed each class, what is the, you can say, different data items corresponding to each variable. So you look at the specific data instance. In your case, the data instance you're looking at is x equal to age less than equal to 30, income equal to median, student equal to yes, credit rating equal to fair. So here, for this data item, which is the line item number which one is that? 1 minute. I'm just trying to see income equal to median. Okay, so basically, I think this is what we're trying to compute here for this particular data item, where age is less than equal to 30, income equal to median, student equal to yes, credit rating equal to fair. Now we know that there are two classes: computer buying yes or computer buying no. So 9 out of 14 is computer buying equal to yes, computer buying no equal to 5 out of 14. Now let us compute, say for this particular data, we had to identify for the age the corresponding variable is age less than equal to 30. So you have to say that what is the conditional probability that having observed that computer is not being bought and age is less than equal to 30, you see that it is equal to 2 out of 9, because out of the 9 computers were being bought, you see that only 2 of them are less than 30. Same way when you look at computer being no, out of the 5 records, only 3 of them are age less than 30. Same thing, you look at income equal to median, out of 9 there are 4. So you try to compute for each of this condition for each of the classes in your particular row which you're considering, or for the data sample which you're considering. So now you want to find out which class should this particular data sample belong. Age less than equal to 30, income equal to median, student equal to yes, credit rating equal to fair. So this is a new data which is coming your way. Now you have to predict it based on the history of this. So what do? You have already computed computational conditions of conditional probability of each of this variable value, which is age equal to 30 or income equal to median or student equal to yes or credit rating for each of the classes, right? Given yes or no. So let's look at the probability that this particular instance buys a computer. In what is the probability that this belongs to this is same as you should look at probability that this particular instance happens and computer gets bought. It is you have to multiply the individual features, which is conditional probability of age, conditional probability of income, conditional probability of student, conditional probability of credit rating with the corresponding value, which is 0.222 for all the S's, right? You take the S, which is 2.222 times 0.444, 0.667, 0.667. So that's what gives you the possibility that given the data you have observed, which is this probability of this actually given computer, if it is yes, then what is the probability of this having occurred is 0.044. Same way we do for this. But now we look at what is the probability of this particular data item occurring. If you find that the probability, the posterior probability given that if computer buying is yes is 0.044 into 0.643, which is what we get as 0.028. Same way with reference to computer equal to no is if you look at 0.019 into 0.357 is 0.007. So if you were to look at a scenario where computer, if you were to assign this to computer buying equal to yes, this particular new row, new instance which has come your way, you get a higher probability which is 0.0828 compared to if you were to do that using a computer equal to no, which would be 0.007. So therefore, you'll say that the new instance which has come your way will belong to computer equal to yes. So this is a bit involved because of the simple reason that I've gone through all the individual probabilities and but intuitively you should think of it like this. Given the new instance which you have got of all the input variables, their values, you try to find out the uh, basically relative probability of each of the classes, and then you find out the class where you have the maximum likelihood, which is the maximum output of the for that particular instance, and then you assign it that particular class. So internally, what is the model? The model is the Bayesian probability which is inherent in your table. That is what is giving you the prediction capability for a new instance. So you see, the power of this is that you are taking a very simple approach of probability and trying to use that for a future prediction. So your history is dictating your future behavior. And that is a very powerful tool in several diagnostic scenarios. Here you are diagnosing a very simple scenario where you're trying to predict the buying behavior of a consumer, whether he'll buy a computer depending upon his age, income, student rate, there is student or credit rating, etc. But in real scenarios, retail companies actually deploy at least hundreds of variables, all kinds of things, seasons, discounts, age, past history of buying, is it buying from this location, all kinds of things, and then they develop complex Bayesian rules to govern how they are able to detect whether somebody is going to purchase something. And that is going to help them in promotion, appropriate trade promotion, in the sense whether they want to promote that particular category of products, like aisle placement could be one, whether they should promote that particular aisle or that kind of products in such specific aisle. So there are different kinds of target output variables you may look, but in terms of the number of arguments they take, here we've taken only 4 arguments. They may take hundreds of such variables. So it becomes a very interesting way to compute potential buying pattern behavior analysis of retail consumers. I'll stop here. We'll do this